Hey, this is video 30.1, and for the next several videos, chapter 30, we'll be looking at where magnetic fields come from. The last three videos, chapter 29, we looked at what effects magnetic fields have on charged particles, and we found that magnetic fields exert forces on moving charges. The equation is magnetic force equals QV cross B. But it turns out that magnetic fields are also created by other moving charges. Just like electric fields are created by charged particles and exert forces on charged particles, magnetic forces are created by moving charges and exert forces on other moving charges. And we're not really going to look at permanent magnets in this class. They're extremely complicated, and there's an awful lot of quantum mechanics you need to analyze them. We're going to confine ourselves to the magnetic field created by electric currents, which of course are moving charges. And we're going to start with a long straight wire. Say it's carrying current that way. And the magnetic field due to this goes in circles around the wire. And not surprisingly, it gets weaker the farther away you are. And we know that the field goes in circles, but which direction? And guess what? It's another variant of the right-hand rule. You point your thumb in the direction of the current, which in this case is to the left, and your fingers then curl around your thumb in the same direction that the field curls around the wire. And so that means in front of the board, this wire would create a field that points upwards. Behind the board, this wire creates a field that points downwards. Up here above the wire, the field points into the board, and below the wire, the field points out of the board. So you need to know the basic shape of the field. We're also going to learn how to calculate the strength of that field, and we're going to learn two ways. In this video, we're going to look at the Biot-Savart Law, and in the next one, we'll look at a much easier method called Ampere's Law. So the Biot-Savart Law, if you have a wire that carries current, and you want to find out the magnetic field at point P, what you do is you break the wire up into a lot of small segments. And so if you look at one segment, ds, ds is actually a vector that points in the direction of the current. And then you can also define the r vector, which points from ds to the point P where you're calculating the field. And the magnetic field dB due to ds is equal to mu naught I divided by 4 pi. Mu naught is called the permeability of free space. It equals 4 pi times 10 to the 7 Tesla meters per ampere. So mu naught I over 4 pi times the quantity ds cross r divided by r cubed. Notice that we've got both r with a vector hat and r without a vector hat on it. R without a vector hat is just the distance, no direction. That's what we've got in the denominator. This ds cross r is a cross product of a vector. Now the magnitude of ds cross r is just r times ds times the sine of theta, where theta is the angle between ds and r. The direction is given by the right-hand rule. Meaning, point your index finger in the direction of ds, curl it or point your other three fingers in the direction of r, your thumb points in the direction of the magnetic field. So for this particular ds, the magnetic field created by this ds is going to point out of the page. And then what you would do is you would integrate over the length of the wire to get the total field. And we'll find that that's doable sometimes, but rarely easy. In fact, we'll look at, there are exactly two cases where the integral is easy to do: a long straight wire and a circular arc of wire. And in this video, we're going to look at the field due to a long straight wire. And when we say long, we mean infinitely long. And so we're going to take a point P there that is a distance r away from the wire. We'll call the middle of the wire s equals 0. This end is negative s. This end of the wire is positive s. And we'll pick a particular ds. So ds points that way, the same direction as the current. And that means that r points from ds to point P, and that angle there is theta. Now our Biot-Savart law says that the field dB equals mu naught I over 4 pi, that's all constants, we don't care, well we do care, but we'll ignore it for now, times ds cross r divided by r cubed. Now the magnitude of ds cross r is r ds sine theta. And the direction of ds cross r, if we point index finger in the direction of ds and other three fingers in the direction of r, the magnetic field points into the page. And the good news is that's true for every point along the wire. Every single ds, the magnetic field due to it will point into the page. So now that we've figured that out, we don't have to worry about the directions of the vectors anymore. Okay, so back to this. Sine theta is equal to opposite over hypotenuse, big R over little r. And so the result is dB is mu naught I over 4 pi times big R ds over r cubed. But what we're going to integrate, we're going to want to integrate over the length of the wire. So our variable of integration has to be s. And this little r does depend on s, so we've got to get rid of that. Little r equals the square root of big R squared plus s squared. So s is that value. And that means dB equals mu naught IR over 4 pi times 1 over r squared plus s squared, all to the 3/2 power. And now we'll integrate it. And to go over the entire length of the wire, s has to go from negative infinity to positive infinity. So we keep all the constants out front of the integral. That's a pi. Negative infinity to positive infinity of 1 over r squared plus s squared to the 3/2 power. Oh, forgot the ds. That's important. And the other thing we'll notice is that this is an even integral. It's symmetrical about the y-axis, which means we can replace it with twice the integral, not 2 pi, 4 pi, twice the integral of 0 to infinity of the same thing. And now to evaluate this integral, we'll make a new slide. I'll write it down. B equals mu naught IR. Combine those factors of 2. Now, this is an integral that is found in the back of your book, or in the front cover of your book. And when we evaluate it, mu naught IR over 2 pi, we come up with s divided by r squared times the square root s squared plus r squared evaluated at 0 and at infinity. Now we can cancel out a factor of r from numerator and denominator. And now, evaluating this is a bit of a pain, because you'll notice, especially evaluating at 0, or at infinity, both top and bottom of the fraction is infinite. Evaluating at 0, both numerator and denominator are also infinite. So you have to be a little bit clever here. So we get mu naught I over 2 pi r. What we'll do is we'll divide the numerator and the denominator by s, which will give us 1 in the numerator. And in the denominator, it'll give us r squared over s squared plus 1, all to the 1/2 power. And I've taken that factor of r out front of the parentheses. When you evaluate this at infinity, that just equals 1, because this little fraction is 0, and so you get 1 over 1, which is 1. And when you evaluate it at 0, it ends up being 0. And the result is the magnetic field of a long straight wire is mu naught over 2 pi r, with direction given by the right-hand rule, as we showed earlier. That is a formula you should memorize. And you should also very much hope that the Biot-Savart Law is not on the AP exam, because it's always a huge pain. In fact, I would almost recommend that you not memorize the Biot-Savart Law and skip any questions you get. There will be no questions on the test where you have to know the Biot-Savart Law. But you do need to know it just so you can see where it comes from, and so that you truly appreciate Ampere's law in the next video. You should memorize that result, mu naught I over 2 pi r. Now if we've got what's called a semi-infinite wire, meaning a wire that goes off to infinity on one end but ends here, and you're finding the field at point P, and that's a distance r, the field at point P is half the value we just derived, mu naught I over 4 pi r. And if you have several wires and you're finding the field due to all of them, you'll use superposition. You find the field due to one, you find the field due to the other one, you add those together. Now what I'm going to check tomorrow are questions 1 and 2, and also problem 1. Problem 18, there's an equation that's derived in problem 16, which you don't need to derive, but you can use the result of 16 to do problem 18. That will make it much, much easier.